All right. Good afternoon, ladies and gentlemen. My name is Qingyan. I am the director of the PolyU Academy for Interdisciplinary Research. So welcome to this pair seminar. And I'd like to introduce our speaker. So our speaker today is Professor YAO Jianping, who is a distinguished university professor at the University of Ottawa. You know, in the US and Canadian system, when you become a university professor, that's normally is the top 10 professors in a university. So it's a very prestigious position. And Professor Yao also is a Canadian research chair in microwave photonics. And he's, of course, a senior fellow at the PolyU Academy for Interdisciplinary Research, we call PAIR. So I think his coming to PolyU will make a very significant contributions to our research, especially on the interdisciplinary research. So Professor Yao, his research interest lie in the microwave photonics, as well as fiber optics and biophotonics. So these include, but not limited to, the photonics processing and generation of microwave signals and arbitrary waveforms, fiber lasers, fiber optic sensors, microfluidics, as well as the imaging and measurement techniques that are based on the coherence of light and radiative sources. So Professor Yao's group has also developed important innovations and concepts that help optimize signal processing performance through speed and resolution enhancement, wavelength tuning, phase noise reduction, and more. For example, the group developed a completely new photonics chip architecture that is Photonics integrated field programmable disk arrays signal processor. So this ultra compact sized and scalable architecture offers more functionalities and achieve ultra fast signal processing with low power consumption. And I believe you know this is a very important contribution to the world. So over years, Professor Yao has authorized and co-authorized over 700 research papers, including the journal papers in esteemed journals like Nature Communications, Science Advances, and Nature Photonics. He has been awarded with multiple prestigious prizes, including the Canadian Discovery Accelerator Supplementary Award from the Natural Sciences and Engineering Research Council of Canada in 2008, and then the R.A. Fessenden Silver Medal from the Institute of Electrical and Electronics Engineer, or IEEE of Canada, in 2018. And most importantly, Professor Yao is a fellow of IEEE, Optical, then the Canadian Academy of Engineering, the Academy of Science of the Royal Society of Canada. So without further ado, ladies and gentlemen, please join me in welcoming our seminar speaker, Professor YAO Jianping.
Okay, thank you very much, Professor Chen. Okay, thank you. Thank you. It's really an honor to be appointed as a senior fellow of PAIRS. And I have been here to PolyU for many times. And I think the first time I came here is almost 20 years ago. And I have, you see, my former colleague, Professor Liu Tao, originally, you see, we worked together in NTU in Singapore. And before the pandemic, I was the departmental advisor, academic advisor, and came here every year. So I know that you see, I see that the progress and a lot of work has been done here, especially in photonics, and that is the area I'm working. So I would like to congratulate that you see that the achievements achieved in the past few years. Okay, so today I would like to take this opportunity to present some of the work that I have been working in an area called microwave photonics. And you see, this is what, you see that this is the topic of my talk. It's photonic integrated circuits for next generation microwave photonic systems. And microwave photonics is a field that we use optics to do things for microwave and to try to solve some problems that could not be solved using electronics. Then we use photonics to solve this problem. And here I would like to start with my presentation by explaining what is microwave photonics. And then that we discuss, because for integration, it is very important to know the material systems. So here I would like to discuss the different material systems for photonic integration. Then that we'll then focus on, you see that photonic integrated M.P systems. M.P means microwave photonics, and for some very important applications. And then finally, I conclude my talk. Although you see that talk is somehow is technical, but I try to make it as easy to follow as possible. Okay, what is microwave photonics? So microwave photonics, usually we say that it's a field that with light. Light means that you see something in photonics. Light as a carrier, and use photonic and optoelectronic devices for the generation, transmission, control, and processing of microwave signals, and to improve microwave devices and systems. So that is, we use light to do things for microwave. And usually a microwave photonic system, you see, this is a system involving, you see that here, the input is a microwave, and in the microwave, we try to convert this microwave signal to the optical domain. So here we use usually a modulator. So here we have a light source, and then the microwave signal is carried by this light at this modulator. And then we do processing, many different types of processing using optics. We do the processing here. And then after processing, we apply the processed signal to a photo detector. Then we get back the microwave. So if we put everything in a box, so you may not know that the processing is done in the photonics domain. But using photonics, we have some advantages. That's why we try to do things, the micro things in the optical domain. And here I show that the reason why we use photonics to do microwave things. And of course, that the major reason is that we solve those bottleneck problems. So limited bandwidth. Photonics bandwidth is broad. It's huge compared to electronics. And to make micro devices and systems to be lighter, smaller, and higher frequency and wider bandwidth. So here, this table shows that a comparison between microwave and photonics. And we see that in terms of bandwidth, it's much wider than electronics. Here you see 2,000 up to 10,000 wider than the microwave. And lightweight means that the fiber, for example, the fiber is much lower, you see lighter compared to a copper cable. And also the loss, the fiber loss is much smaller. It's 0.2 dB per kilometer. So we use fiber now for all the communications now, especially long haul communications. But you see that the cable loss is huge. So the distance is very short. And then another very important feature is that photonics, we do not have those, you see, electronic interference. It is immune to electromagnetic interference. And then currently you see that we have photonic integrated circuits. So then we can make a microwave photonic system using photonics to make the system smaller. And finally, we can using optics, the parallel processing ability, which is unique for optics, to increase, for example, the bandwidth or increase the speed. And then that for microwave photonic systems in the past 30 years, so most of the systems were implemented based on discrete components, so individual components. So the system is very heavy, very high costly, and also the stability is also a problem. So then people try to do the integration. So here you see that I'm going to discuss the different material system for photonic integration. So usually we have 4 different major material systems. The first one is called the indium phosphide. Second one is the silicon nitride. And then the third one is the lithium niobate on insulator. And the last one, the silicon insulator. So we see the first one. So that's why you see the indium phosphide. That is the one widely used in photonic components. So you can, for example, lasers. Here, I'm using here laser pointer. You see that it's produced by this material. So it can be used to integrate both active and passive photonic components. So almost all components can be done by this device, but the problem is that it has a higher loss and a large size, and also it's difficult to integrate with electronics, for example, CMOS, for example. Then another material system is called silicon nitride. So silicon nitride is the key feature of this material is that the loss is very small. So waveguide loss is very small. So for integration, so then we may, sometimes the loss is a key issue, then we may use this material. But the problem with this device is that it cannot be used to develop, for example, this light source. It cannot generate light. And it cannot be used to for example, to develop modulators, amplifiers, photodetectors, cannot do it. So then the only, you see, we can use it for these passive components, like a filter or coupler, all those. This second material system. The third one is lithium niobate on insulator. So this is very good material, especially you see that we use this for modulators. It can work at a very high frequency. And also that, especially recently work on this thin film lithium niobate. So that one, the bandwidth can be very wide, and the efficiency, we call the VPI, the efficiency is very good, especially for microwave photonic applications, microwave photonics applications, that this is very important. That is a second material system. A third one, the last one is silicon insulator. So this is we usually call that silicon photonics. So this is very good because it's CMOS compatible. So then all the technology developed for CMOS for the IC currently we're using, for example, in the mobile phone, in the computer, we may use the same, you see the process to produce these photonic devices. And most of the optical components, both passive and active, can be supported. So the advantage include that a small footprint, low loss, and simple fabrication process because it is CMOS compatible, and it can be integrated with electronics because you see CMOS, we do the electronics and on both analog and digital. So, but the only limitation that is also is very key that the limit to this wide application is that it cannot be used to generate light. So silicon cannot be used material to generate light. So that's why for the integration of the system, then we have to use so-called hybrid integration. That means that with different materials. So, but we said that this silicon nitride, and the lithium niobate, these 3 material systems, you see, play a very important role in microwave photonic systems. So today I will give some examples of the use of these materials for microwave photonic systems. So here we start with the first one. So it's called two-time delay beamforming. So what is two-time delay beamforming? So we know that if, for example, here, this shows, this is a phasor antenna. So phasor antenna compare to, you see the conventional antenna, you can see the antenna is rotating. So that is many years ago. For example, starting last century, for example, But now you see with this phase array, so the beam is scanning here electronically at a very high speed, but no mechanical movement is involved. Then how to do that? That is use so-called the phase, for example here, phase shifters. So if you look at this, so this is in fact this is a phase. You see the phase shifters, and if for example here, and if you change the phase, delta phi, 2 times delta phi, 3 times delta phi, 4 times. If delta phi equal to 0, for example, 0, 0, 0, 0. So that this RF signal with no, you see, with no phase delay for the 4 channels. So then when we radiate this micro signal to the space, because they have an identical phase along this vertical plane, and then the microwave in the free space, they will interfere, and along this horizontal direction, they have the highest you see, constructed interference. So then the beam will be pointing to this horizontal direction. But if this delta phi is not 0, either positive or negative, and based on this equation, we can calculate the beam pointing direction theta here. So which is a function of delta phi. You change delta phi, then the beam is scanned. So this is the fundamental principle of a phase array antenna. But this is a conventional way to implement a phase array antenna using these phase shifters. But the problem with this approach is that it has a problem which is called the beam squint. Beam squint means that if you look at the expression here, so although we change delta phi, theta is changed. But here we have lambda. Lambda means that this RF, that is the wavelength or the frequency. So which is the theta, not only a function of delta phi, but a function of the frequency. So that means that for RF signal, usually for radar, for example, radar pulse we do the Fourier transform. We have a spectrum. The spectrum could be very wide. So for different spectrum components, this theta may be different. So the beam is you see that it's not pointing to the same direction. That is the beam squint problem. So this problem can be solved simply by using this, replace these phase shifters by the delay lines. And this time, if we look at this equation here, theta, this beam pointing direction now is only a function of tau. Tau is here. This is the tau here. But it is from here, you cannot see this lambda here. So it's not a function of the wavelength or the frequency. So then we do not have this beam squint problem. So all the frequency components will be pointing exactly the same direction. So that is the motivation. That is why we use true time delay. So that is called, this is a true time delay. So how to implement the true time delay? Using photonics. So here I give a simple example here. So for example here, so this is an RF signal. This signal will be radiated by this antenna to the free space. And this is a tunable laser source. The wavelength can be tuned. So then here's a modulator. So that means that this micro signal is modulated on the optical carrier and then sent, for example, here to this. This is called the true time delay lines. And here, this is this you see here. This black box is called fiber Bragg gratings. It's kind of wavelength selective filter. So only, for example, if we tune this wavelength, for example here, this wavelength is lambda 3. So all the, you see the wavelengths, all these 4 channels will be reflected along this lambda 3. And then send for the detector, get back the microwave, and through this T transmitter R receiver, this TR module, and then send the free space. So for example, if we tune the wavelengths at lambda 3, the light will be reflected along this vertical plane, and then at the beam at this vertical plane will have identical phase, or identical time delay, then the beam will be pointing to the horizontal directions. But now, if we tune the wavelengths to lambda 1, for example here, then the light will be reflected along this plane, Then finally, the beam pointing direction will be perpendicular to this plane here. So the beam is scanned. So very simple. Simply tune this 2 mm source. Then you get the beam scanned at a very high speed. But this is a way using fiber optics. But fiber optics sometimes is very sensitive to environment. So it's not very stable. So people, for example, here in this in France, you see that it's a Thales. Thales is a company where they try to do these radars for many different applications. So they try to develop a system using free space optics. So free space optics the size is large, of course, but it's very stable. So then the different time delays are achieved. For example, the light depends on the polarization. Either, for example, for this polarization here, this one, it is this polarization, the beam will be, you see, reflected by this beam splitter, go through a longer distance. Or this polarization, so this polarization, then that the beam will pass directly through this prism, okay, splitter. So you get different time delays. So this is the way. So using free space optics. So then that they did some experiment and show that they do not have this beam squint problem. So for example, they do the frequency from 2.7 gigahertz to 3.1 gigahertz. That is quite a large bandwidth. So then they measure the beam pointing direction. You see that for all the frequencies, and you see from this range, this 2.7, 3.1. So always pointing to the same direction. So no beam squint problem. But the size is huge. Then another way to make the size smaller, and the people try to, for example, use the MEMS switch, this MEMS switch. So this, you get different time delay. The time delay can be, if, for example, for this switch, if it is a bar state, that light go directly. Or the cross state, the light will go through a delay line. Okay, so it depends on the states of these switches. So then that you get different time delays. So I just give one example here. For example, here, the one here, and bar. So for all the switches in the bar state, so all light go this way. You see here, no time delay, no additional time delay introduced by the delay line. No. And here we have an offset delay line, which is 3 delta tau. But here you see that they go straight, and we do not have this 3 delta tau. And the difference between these two channels is here is 0 minus 3 delta tau. So then you get minus 3 delta tau. And another, for example, states we cross, for example. Cross, then you have a tau 1, tau 2, tau 3 plus 3 delta tau. That is the total time delay. And here is tau 1, tau 2, tau 3. But here you have a delta tau, 2 times delta tau, 4 times delta tau. Totally is 7 delta tau. So 7 minus this 3, you get 4. So you get the 4 here. So then finally you get different time delays. And here for this switch 3, you see here 3 switches, you have a total time delay as 2 to the power of 3. That is 8. The 2-bit. We said 2-bit different time delays. But this is based on the switch, but the size is still large. So then people try to using photonic integrated circuits. So this is the work done recently, and exactly the same architecture. The only difference is that you try to implement it using silicon photonics. For example, here this is this blue box. That blue box is a switch. So the switch could be cross or bar states. And then here is the time delay. So tau 2 times the delta tau. And here this is this one is the offset time delay. So exactly same architecture, but only the implementation is done using photonic integrated circuits. Okay, so that is the circuit. For example, here we look at so here the light is coming, and through this splitter, it's a power splitter into 8 channels. You have 8 channels. And then that this the delay lines is called the offset delay lines. And then here, this is the true time delay. So true time delay lines. So they put them together. So there is a true time delay beamforming system, and this is 8 channel. but this is integrated. The size could be much smaller, much smaller. But if we want to make the size even smaller, so another approach is using this so-called resonators. Resonators. You see that if this is resonator. The resonator you see here, this is the frequency, but here is group delay. So resonator, if we measure the spectrum response, you will see that the resonator within that, you see the resonance. You have also you see group delay, different time delays. So then we may use this as a delay line. The size could be much, much smaller than the actual delay line. So if the bandwidth, you want wide bandwidth, you may use a few this resonators cascaded, but with certain offset frequencies. Then the bandwidth could be large. So the good thing is that the bandwidth, the size is smaller. So this shows that 1/8 beamforming network using these resonators. The size could be much, much smaller. And for example, to get different time delays, you can get different time delays through this, usually it's a thermal tuning. You change this, by change the temperature to change that, the resonance, you get different time delays. So this shows that it's a 1/16 beamforming network. And the one here, at the beginning, I said that silicon itself, no light can be generated. But for this two-time delay beamforming system, we need light source. We need the modulators. We need the photodetectors. And also, we need the delay lines. So we see this is, in fact, is a two-time delay. This is a two-time delay optical beamforming network based on hybrid, this hybrid indium phosphide and silicon. So two different materials, silicon nitride. So you see that here, this is light source, this is a laser. You see here it's a gain, the GS, gain source. So you have the gain, and here this is using silicon nitride. At the very beginning, I said that silicon nitride, the loss is very small. The Q factor is high. So it's very good to use it as a filter to select the lasing wavelengths. Okay, so this is a light source, and then here we have this indium phosphide two-phase modulators. Put them together, you see, connected in parallel, which is equivalent to a Mach-Zehnder, called Mach-Zehnder modulator. It's a modulator, and then this modulated signal, and here is a filter, means that the modulation usually is a double sideband. We have carrier plus two sideband. But if we remove one sideband, which is called a single sideband, it's you can save the spectrum. You see that to make a spectrum, save the spectrum, the efficiency by increased by 2 times. So that's why they use a single sideband filter to remove one sideband, and then go through these delay lines. This is in fact is a ring resonator, and then apply to the photodetector. So this through thermal tuning, you get different time delays. So this is in fact is a hybrid system, consists of either the indium phosphide. You see here the indium phosphide for the gain, and here for the optical filter, it's silicon nitride. Silicon nitride because loss is very small. So here delay line also is a silicon nitride. And the photodetector, you use indium phosphide. And here shows that the chip, you see that you can see that for A here is the indium phosphide gain section here. This is the gain section, very small. And B is that this is delay line. This is the delay line. And you have phase modulators C that forms this Mach-Zehnder modulator. And the photodetector here, D, is very small here. So in that different, you see two different material systems to form this beamforming network. Okay, so that is the first example to show, you see that the beamforming. So beamforming, so to achieve different time delays, it's very simple, different time delays. And second example is called optoelectronic oscillator. Oscillator we know. So this is in fact is an electronic oscillator. So in electronics, for example, we know that this is a transistor. provide gain. And this LC circuit, we have a resonant frequency. So this is used for frequency selection. And the frequency that you see here, we have the transformer to couple the output to the input. If you see, if it is positive feedback, and if the gain is sufficiently high, then it can oscillate. And the frequency is determined by this LC. And but this electronic oscillator has some problem, especially the Q factor here is not very large, especially for this inductor, for example. For example, inductor, it have resistance, very high resistance. The Q is not very large. So then the quality of microwave signal, usually we say the phase noise is high. It's not very good. So for applications such as radar, so we need high quality microwave. So this can be done using this so-called optoelectronic oscillator. So why it can do the work? The reason is that because we have this feedback loop, you see feedback loop, and we have a gain. And here we may use a filter to do this frequency selection. The motivation of using it is that we have this optical path before this photodetector is optical path, and this fiber could be long, and the fiber loss is very small, we said, very, very small. So long fiber, usually the Q factor is large, and the phase noise is low. So fiber loss is very, very small. So for example, we can use 10 kilometers of fiber without any problem because the fiber loss is 0.2 dB per kilometer. 10 kilometers, 0.2 multiplied by 10 is only 2 dB loss. It's a very small loss. Okay, so that is why people try to use this optoelectronic oscillator to generate a microwave signal. But if we want to generate a microwave signal using a 10-kilometer fiber, the size is still large. You see the oscillator is very large. So people try to replace this fiber by, for example, here, this is a whispering gallery mode resonator. So this kind of resonator can be made to have very high Q factor, for example, 10 to the power of 8, very high factor, which is equivalent to long fiber more than 10 kilometers, for example. So the oscillator itself can be made small. So for example, if you look at this one, this is very small. This is by a company, it's called OE waves, very small. But if you look at in detail here, it is not integrated. It still uses PCB. It's PCB, although it's very small, but it uses PCB. So the fabrication is it's not easy. You see, not easy. The size is still large. So then we try to do the integration. So for example, this is the work we did quite a few years ago. So use silicon photonics. For example, we can implement the phase modulator using silicon. The filter here, we use a filter to do the frequency selection using silicon, and the photodetector also use silicon. So then 3 devices on the same chip, silicon. But we said already that silicon cannot generate light. So then we have to use a LD, which is external. So for example, this could be implemented by indium phosphide. And also the power amplifiers. Ideally, you see, these amplifiers can be implemented by silicon because silicon can do amplifiers. But at this moment that the processing technology usually has not yet been ready to do the photonic devices and also do the analog electronics devices. But this can be done, I think, quickly in the future. So then that this is a partially integrated optoelectronic oscillator. And we can generate micro signals at very high frequency, usually from a few gigahertz to tens of gigahertz, even hundreds of gigahertz. This is integrated. And that is based on silicon. But if we want to further increase the oscillation frequency, for example, the one here I showed, see here, the one here, this frequency can be, for example, 20 gigahertz. Silicon photonics usually cannot be too high frequency. So solution that is to use this thin film lithium niobate. So this is the work done, I believe, in Guangzhou, Zhongshan University. So they try to replace by this silicon modulator by this lithium niobate modulator. And here, this resonator for frequency selection using this silicon, using this lithium niobate. But again, I said that laser, you see, light cannot be generated by this lithium niobate. And the amplifier cannot be done. So that means that there is a partial integration. So then that you can use this to generate microwave at higher frequencies, higher frequency. So this shows that this is the modulator. This is the modulator. Okay. So then if we really want to implement a fully integrated optoelectronic oscillator, then that we may need to use different material system. So sometimes we call that heterogeneous integration. So light source, for example, we use indium phosphide. Modulator, you can use silicon or lithium niobate. And the photodetector, you may use indium phosphide or silicon. And high Q optical filter, usually the Q should be high. So we use silicon nitride because the loss is small. And finally, electronics. For example, amplifier here, you use silicon. Okay. So then heterogeneous integration is very important, but people are working very hard at this moment and try to make it work. And then another example I would like to share is that the programmable signal processors. Okay, so here I show that this is the one. It's called a fully reconfigurable waveguide Bragg gratings for programmable photonic signal processing. So this is the fiber Bragg gratings. Here in PolyU is that we have a strong group working in these fiber Bragg gratings. For example, here this is a fiber Bragg gratings. Fiber Bragg grating. This is called uniform. Uniform means that the period identical. So uniform, and you may get, for example, this is a reflection spectrum. And here, if you introduce here a pi phase shift in between, here you see the spacing is increased. You may get a so-called phase shifted. Phase shifted means that you can introduce a very narrow notch here. Or if you change this period linearly by increasing or decreasing the period linearly, and then you get a so-called linearly chirped fiber Bragg grating. So, but for this fiber Bragg gratings, a lot of applications in optical communications and also in sensors. But usually when a grating here, fiber Bragg grating is developed, usually it cannot be tuned. You cannot change the spectrum response easily. You can stretch it, but that is the only way usually you can do. So then we propose using silicon photonics to design, you see, this waveguide grating, and the spectrum response can be programmable. So this is what we do is that we start from wafer, and we have grating and doping. The doping means that through this doping, then we apply electrodes. And then if we have an injection current into this section, for example, here, that then the refractive index could be changed. And then we can apply voltage control to control these different sections. And then we may get programmable gratings. Again, I show a few examples, for example, here. The first one. For example, here, this is the grating. Grating is, you see, it's a periodic change of the refractive index. Grating is a periodic change of the refractive index. And if, for example, we do not apply any voltage, so that means that you see here, the refractive index is here, you see, flat, identical. This is like a uniform fiber grating, but in between you have a phase shift. So this is a phase shift FBG. So then you get a spectrum response which corresponds to a phase shift FBG. And if now you apply strong, you see, current to these sections to disable, because current is very, very large, then the loss become huge. The loss is huge. So light cannot reach, you see here, reflected. Cannot. All the light is absorbed. Then this only half is functional. So this is a uniform FBG. So uniform grating. Okay. And if, for example, we apply the current to change the refractive index, increasing linearly, so then this become a chirp grating. So that is the way to, through this voltage control, you can get different type of gratings with different spectral response. So that is the fabricated device, and we get the spectral measurement. So I will not go one by one, but from here in general, you see that we can get different spectral response, and you can get a chirped one. You can get, for example, here this one is a phase shifted grating. So many different types of grating you can get through a single programmable grating. So that is one example using silicon photonics. And here is another example using, you see that also silicon photonics, which is called multi-purpose silicon photonic single processor core. So this one, we look at the architecture here. I'll make it bigger. You see, you can see we have an optical source. Usually for a microwave system, at very good beginning, I said, we need a source, we need a modulator, and here's a processing unit. You do the processing here, and here is the photodetector. Then you get the output. The output is microwave, and the input is microwave. Okay. So for this particular example here, they try to you see that do the reconfigure this, you see, reconfigure optical core, use this one. Reconfigure this optical core to get different signal processing functions. So here I give, this is a fabricated device. See here, this is a fabricated device. I will show you the examples that how this is used for different signal processing. For example here, and this is you see, this is the network here. They can be reconfigured. For example, this line here can be the light go through, and it's not disabled. You can disable the line. Here it's not disabled. Go up here, then go back here, or the second channel going down here. So that is you can see that this is like a two-type filter. It's a kind of delay line filter, two-type, and you can do this if this is go further up. Also it's a two-type, but the difference, the time delay difference is different. So the spectrum response, of course, is different. Or you can reconfigure it as a three-type filter, three-type. So this is the spectrum of three-type filters. So that means that for this device, you can do the using, you see that the reconfigurable core to get a different frequency response for signal processing. Here's another example, also using silicon photonics, which you see that you see this you see the micro disks, all this is connected. So this is something similar to an electronic FPGA. So that can be programmable for different signal processings. This is the work we did it a few years ago. And here, one example of the application is the two-time delay beamforming. For example, here, this disk is get the time delay, and here two disks, we can get the two-time time delay, and 3 times, 4 times. So then that by tuning the time delays, you can get different, you see the beam pointing direction. Beam pointing direction can be scanned. So that means this is one possible application using this disk single processor. Again, so for the implementation of the entire system using on a single chip, so you have to use the heterogeneous integration. So that is the work we have to do at this moment. And the last example is called microwave radar. So integrated microwave radar systems. Okay, so then you see that. So I think in 2014, a paper was published. It's called fully photonic-based coherent radar system. Since then, a lot of work has been done using photonics to do micro radars. And the principle is quite simple. I'll quickly go through it. For example, this is a radar system. For example, here we have a VCO, voltage controlled oscillator. And using this, for example, this sawtooth to control this oscillator, we generate the chirp, the linear frequency modulated chirped waveform. And this waveform radiates to space, because when you hit your target and reflected, you have time delay. So for example, this is delayed. This is received waveform, and these two apply to, for example, here mixer, the bit where you get the frequency difference, which is delta F here. This is delta F. By measuring delta F, you know the distance. So the distance is longer. The delta F is bigger. So this is in fact is a radar system. Very simple. And then by simply measure the delta F, for example, here, a different distance, you get a different frequency. You know the distance of the target. And using photonics, why? The reason is that here, the range resolution, if you look at this equation, which is inversely proportional to the bandwidth. The bandwidth is wider and the resolution is higher. So the number is smaller, but the resolution is high. And this is the key reason using microwave photonics. And for example here, this is an example. It is work done, I think, in 2017. And using photonics, you see that to implement a radar system, so they use a modulator. Then they try to, the key advantage in using microwave photonics is that we can generate broadband signals. For example, here, we use a low speed signal generator. You get a chirped waveform from 4.5 to 6.5. But using this microwave photonics, you can 4 times increase the bandwidth. So this is a way using photonics. So the bandwidth is increased. Then that you can increase the resolution. For example, you have two objects. You see it, 1, 2. Then you get the 2 reflection peaks to measure the difference between the two. You know the distance between these two targets. Okay. So and using this approach, also you can do the imaging. For example, this is the electrical fan. When it is moving, you can use this radar to get the image of this fan. And almost at the same time, by another group. So the earlier group is from Nanjing University of Nanhang University. And this one, the second one is by the Chinese Academy of Sciences. Almost the same time. You see that it uses microphotonics radar and do the imaging of this Boeing 737, I think in Beijing airport. And this is the image using the radar. So the quality, I was told that quality compared to electronics is much better. And then how to do the integration. So this is almost finished my talk. And it's because we may use, you see that all the implementation earlier, just to work earlier is by discrete components. Then people try to use integrate solutions. For example, this is the work very recently. This is the work, I think it's a collaboration between Nankai University and the CTU here in Hong Kong. Using, you see that's the lithium niobate, because the lithium niobate modulator can operate at higher frequencies. So they try to implement these 2 modulators. If you look at the architecture here, 2 modulators are involved. This is modulator and this modulator. And then this niobate is a really good material, especially for high frequency modulation and also for high modulation efficiency. The VPI can be very small. So that is the work done very recently. And it's called, you see, integrated lithium niobate photonic millimeter wave radar, and published very recent, I think just a few weeks ago. Okay, finally, conclusion. So there is very good things for photonic integration, such as you see the size is smaller, bandwidth is wider, and loss is smaller, and functionality compared to discrete components integrated also. Functionality is higher, and the scalability is higher, and also enabling advanced applications. But as I said, that the key challenge is that the heterogeneous integration. So that is it's not yet ready, but people are working very hard, try to use different material system to implement a system on chip. So that is a challenge, but also the opportunities. Thank you very much. Thank you.
YAO has just given us a very exciting talk about the integrated circuit for microwave photonics. Are there any questions from the floor?
Okay, very exciting talk. And I believe it will be very inspiring to our student working on photonics, sensors, communications. Now, you have give talks in several aspects. So my first question is regarding this true delay line, right? You use the photonic optical delay, right? For different wavelengths have different delay to actually steering microwave signals. By doing this, actually, you can make the phase of the microwave signal independent of the delay, right?
Correct. Yes, correct.
So my understanding become another area. So my question is, you use example 4 channels to form or to steering the beams.
Yes.
My question is, in real applications, is 4 channels sufficient? Do you need how many channels? Can you tune a delay over a certain range of time? And how do you tune?
Okay, thank you very much. Thank you, Prof. Jing, for the question. Very, very good question, you see. The 4 channels is simply for the university lab demonstration. For real applications that we need hundreds of channels, even thousands of channels, because we want to get a very sharp beam. So that means that for example, optical interference, if you have many, for example, from optical interference, if you have the interference of many different channels, then you get a beam smaller. And the same thing, you need many channels. Then the challenge is that for so many channels, for the discrete components, it's very difficult. So that's why this concept has been there for 30 years, but not major applications. So that's why people have to work very hard, try to use the photonic integrated circuits. Then it is possible. It is possible that to have many channels, at least hundreds of channels. So that is your first question, I guess. The second one is the time delay. So time delay, I think that we can get many as large as you want. That is not a big challenge. The challenge is that it's many channels, and the loss is the challenge. The loss because for example that here example I use 3 switches cascaded. That is correspond 8 different time delays, 8 different. But if you want the beams scan the beam, you see that means it's only 8 different angles. So if we want to increase the resolution, scan smoothly, you may need, for example, 8 different switches. So that means 8 switches cascaded. The loss is a problem. Yeah. So that's for integration. We have to either to increase the number of components and also to reduce the loss.
Use optical loss.
Optical loss, yes. Because the optical switches, in one switch you have a loss, and you have, for example, 8 switches cascaded. So the loss is usually huge. It's very large loss. Yes.
Any other questions? Okay, I have one question.
Sure,
I think because certainly microwave photonics offer many advantages, and but then at the same time in a lot of areas it's a direct competing with electronic, like optoelectronic oscillator. You're competing with the frequency synthesizer, and then microphotonic radar, you're competing with the traditional radar. And so what are the main challenges that, I mean, certainly, I know that in certain application, in what kind of application like microphotonic is probably will be thought like you have a comparative much important competitive advantage for it to be used. Yeah, and or what we need to do in order to make it to replace. And I mean, certainly integration is a good way to go. And then what are the challenges for us to overcome for it to be completed in many situations completely replace its electronic counterpart.
Okay, thank you.
Yeah.
Thank you very much for the question. You see, for example, micro generation, you just ask the micro generation. We use oscillator. We know for electronics we use like for example is a pulse oscillator. They can generate microwave with very good. For example, this the watch, electronic watch, we have the oscillator inside. So, but usually the frequency use a pulse oscillator is generate frequency low. For example, 10 megahertz. But if we want to get 10 gigahertz, so you use a frequency synthesizer. Usually we do frequency multiplication. So from 10 megahertz to 10 gigahertz, that's 1,000 times. So when you do this multiplication, so usually 2 times increase the frequency, then the phase noise is reduced by 6 dB. So that means that it's 1,000 times is 20 log, and 1,000, I think it's 60 dB. 60 dB loss in terms of phase noise. So for example, originally generate phase noise is minus 120 dBc per hertz at 10 kilohertz offset. That usually we say this way. And minus 120 dB become 60 dB. So this is the major challenge. So using synthesizer to generate very high frequency, I think that the phase noise performance is not good. So in optics, we simply, for example, we have a simpler way, so to beat 2 wavelengths to generate microwave. For example, 1550 nanometer for optical communication wavelengths. So if the wavelength difference is 1 nanometer, the bit frequency is 125 gigahertz. So we do not use these multiplications. The phase noise performance is not reduced. But to really replace electronic devices, I think that at this moment it's still very expensive. Using microphotonic discrete component microsystem is expensive. The size is still large. For example, this optoelectronic oscillator, this size, like a laptop, for example, and for some applications it's still large. For example, airborne application, aircraft. So people want that very small. So that's why we have to use photonic integration to make the size smaller and the stability, improved stability, and the cost also reduced. So I think it's the key solution to make microwave photonics for wide applications as the integration. Yeah.
Thank you. Any other questions?
Oh, hello, Professor. I'm from CTU. My research direction is lithium niobate, and I want to ask, for a microwave photonic systems, which platform, such as lithium niobate, silicon platform, and the indium phosphide platform, and will have a greater advantage in the future development?
Okay, thank you. So I think that for the system on chip, for example, system on chip, microwave photonic systems on chip, I think that the major platform should be silicon. It's my personal understanding is silicon, and most of the components, if you can use silicon, do it in silicon. And then that for modulation, for example, if we want to achieve very high wide bandwidth modulation, perhaps then you use lithium niobate. So lithium niobate on silicon, you can do that. So currently at this moment that the lithium niobate could be thin film could be done with silicon, that for modulation. And then for the light source, indium phosphide. So either use hybrid integration. Hybrid integration means that perhaps it's for example, we have a indium phosphide chip. We have silicon chip. The two chips is through this photonic wire bonding to couple the light into the silicon chip. So this is called hybrid integration. But the heterogeneous integration, perhaps you have one platform, you grow this indium phosphide on the silicon. So that's more challenging. So I think at this moment, I think that two approaches. A simple approach is we have different chips and all the chips connected through this wire bonding. So that is, we have this wire bonding machine and people can do that at this moment. Another one is that we grow these different materials on the silicon platform. That is more challenging. And I think the processing is very complicated and costly. Yeah, thank you.
Any other questions?
Thank you. Thank you, Professor Yao. Thank you for your very informative. Thank you for your very informative presentation. And I'm a PhD student in PolyU, and I'm very excited today because I have read many of your review papers before. I have read about the microwave photonics, microwave photonic sensors, microwave photonic systems, photonic-based broadband microwave measurements. So I'm very excited today. Yeah, and I want to express my gratitude for you for your review papers. Yeah, and I'm currently exploring the microwave photonic in refractometry system, and I have applied this microwave photonic technique in PCB defect detections. Yeah, many of the microwave photonic are applied in radar system, but I try to explore it in the refractometry system. Yeah. Currently, the microwave generation is based on optical frequency loop technique. And I have one question about this. If I want to further my research, I want to increase the bandwidth of the microwave signal and the signal noise ratio based on the optical frequency loop technique. Do you have any recommendation that I can pay more attention to? Yeah.
Okay, thank you very much. So thank you for, you see that you read many of my papers. It's true, you see all the papers names, you still remember.
Yeah.
Thank you. And for the micro generation, currently, for example, the radars, for example, that the two examples I gave here, it's based on this frequency multiplication using Mach-Zehnder modulator. So that is the simplest way. So we generate small bandwidth micro signal using electronics, and then we try to use frequency multiplication. 2 times the bandwidth is doubled, 4 times the bandwidth. That is the simplest way. But if we want to generate the simplest way and the most cost-effective way. But if you want for research, of course, you try to do something different, and you can get your papers published in a high impact journals. I guess perhaps you have to work using optoelectronic oscillator to generate. Because an optoelectronic oscillator at the very beginning, we use it to generate a single frequency micro signal. But this oscillator can also be used to generate, for example, chirped microwave, even very broadband chirped microwave. So some papers published in the last 2 or 3 years. So perhaps you can read the papers. One paper is called Fourier domain Fourier domain monolocking in optoelectronic oscillators. So you can generate one bandwidth micro waveforms.
Yeah, in addition to my question, I have already conducted an experiment based on the optical frequency loop technique. We are able to generate the step frequency signal with a bandwidth of 16 gigahertz. And we applied this wideband signal into the PCB defect detection.
Okay.
Yeah, and in the experiment, we are able to identify 3 defects of PCB circuits. And now I want to apply this technique into the integrated chips defect detection.
Mhm.
So that means that we need wider microwave signal.
Yeah.
Yeah. So I have tried many other system configuration. I have already done the simulations.
Okay.
But if I want to further this research, is it better to change the system configuration, or is it to apply the previous system configuration but in other areas?
Okay. So I think perhaps first you have to
Mm.
calculate what is really the bandwidth you need to do this detection. For example, the feature size is this size. What is bandwidth is needed? So then from that requirement, perhaps you think what is technology you need to use. For example, currently you said that the bandwidth is 16.
Yeah.
So 16 is not large enough. Then perhaps you can double it by 32. I'm not sure. So I guess perhaps firstly you may do some calculation to see what is really the bandwidth needed. If we, for example, need 200 gigahertz, that is difficult to achieve. Then you may find some other solution. Yeah.
So it's better to try other system
First,
configuration.
you have a value, the theoretical value needed. Then you see this can be practical or not practical.
Okay. Yeah. Thank you.
Thank you.
Any other questions?
Thank you, Professor Yao, for your exciting talk. Our group currently have developed a chaotic wavelength sweep laser, and I wonder if it can be applied in your true time delay radar system.
Okay, thank you. You see, for radar, you see, radar, we have usually for radar, usually we use the chirp waveform for detection. We send a chirp waveform, and we get back. We do the pulse compression, and then that we can get the measurement of the distance with a high resolution because chirp waveform can be compressed. So that is another way is that use so-called noise radar. So noise radar is that, for example, you radiate this or noise. For example, the noise, you do the pulse compression, and the noise can be also very significantly compressed, including, for example, chaotic signal. You send a chaotic signal, and when you receive it back, you do the correlation, you can get pulse compression. And perhaps this chaotic signal, you know it yourself, or other people may not know it. So it's good for security, I guess.
Any other questions?
Thanks for the wonderful talk. So I have questions about that. As we all know, the microwave photonic systems have a lot of advantages. However, it also faces some challenges, such as the loss and efficiency. So my question is that, what do you think the microwave photonics can be used in the which application can be used in the near future? I mean, in the benefit of daily life. So, so this is my question.
Okay. Thank you. I think it's simply simplest implementation. It's the microwave photonic filter oscillator. That is a very simple microphotonic system, and this and also can find many applications. So if we can do this, use silicon for integrated circuits to implement this microwave photonic oscillator, so optoelectronic oscillator. So this could be the application that can be implemented in the very near future. I believe. But true-time delay is still challenging because you need a lot of components, and the loss is really it's an issue because we said that you have many stages cascaded, so the loss is an issue. For true-time delay, I guess a major breakthrough has to be done to reduce the noise, the loss, to reduce the loss. But optoelectronic oscillator could be done relatively simple. Yeah.
Oh, I have another question. Is that because for many years, one of the another major challenge for microwave photonics is the loss incurred by changing from RF to optical back to RF. But now with the advancement of devices like you reduce VPI for modulator and so on, and so I was told, and also you can have a higher power because you have a high power unidirectional traveling diode, photodiode, yeah, so UTP and UTD, yeah. So I was told the loss can be reduced to 0 dB. I'm not too sure. What's the typical state of the art conversion loss from RF to optical, then back to RF? Now, for the state of
Thank you. That is the key challenge. You see, for microwave photonic system, we have modulator, we have photodetector. So in that usually the loss in the past, for example, it's 30 dB loss, even higher. The reason is that for modulator, the VPI is large, and for the detector, the input power cannot be very large. So then now you see for this niobate, I guess the VPI can be much smaller, so the efficiency is higher. And for high power handling, PD is now available, so then the loss can be reduced. And if we can incorporate some amplifier in between, so the inner loss could be reduced. But still, it's a problem at this moment.
So it still cannot achieve 0 dB.
No,
No. Yes.
So.
Okay. Someone told me can achieve 0 dB. So I was just wondering because I haven't really followed.
For the detector, you need high power and handling power. The photodetector is very, very important.
Yeah. Any other questions? Yes.
A follow-up question for the photonic microwave resonator. I noticed the resonator actually started from the modulator, fiber, and filter detector. They form a loop,
yes.
Right? So how does the performance of the laser affect the, or do you have any requirement for the laser source?
Yes.
Because it is not in a loop, right?
Yes, it's not, but yes. So this also, you see that very good question. For the laser source, for example, we have a ring noise. So that noise will be translated to the microwave generated. So then you want to generate a microwave high quality with very small noise, then you need to use laser that with small, for example, the ring noise, and also the phase noise of the laser will also translate it to the microwave. So the quality of laser source is important also.
Yeah, I have another question about the OEO. Yeah, sorry. It because in OEO you need a very high Q filter.
Yeah.
Okay, and you mentioned you can use a long fiber. Then you can. I think people also are using a very high Q resonator.
Yes.
Yeah. What which probably or likely to give you a very low phase noise now? Yeah.
And I think it's fiber definitely can have non-fiber can have a lower phase noise.
Okay.
And even you see the resonator have very high Q factor. For example, the one here by the OE Wave in the company is they can generate a 10 gigahertz microwave. The phase noise is around 90, minus 90. But fiber can easily get minus 120.
And also fiber is probably more stable. Yeah, because the Q resonator, you really have to align with the wavelength. Yeah.
Temperature control.
Yeah.
Package is an issue.
Yeah.
Packaging. Yeah.
Okay.
But the fiber is the size is too large.
Yeah, yeah. So
Yes.
it really depends on application. Yeah. Any other questions? Or any other, and not necessarily to be related to the scientific topic. Like student, you want to be asked why you have been so successful to become a famous professor, or what you need to do as a PhD student and other things. Yeah, yeah.
Thank you very much, Professor Yao. Your brilliant talk has given me many inspiration. Actually, I'm a researcher in electronics, not the photonics, but I have one question I'm very curious about it. You just said in the true time delay, the figure maybe put later, we need to control the loss in different stage cascaded. And I wonder if we predefine the time delay we needed, and if the loss can be calculated in some simulation software, and if we can do the compensation in the detector, we can use different detector to compensate the loss, and we can reconstruct the signal amplitude we needed. That's my question. Is if because I'm not working in this area, so if I'm sorry. Thank you.
Thank you. I understand your question. So yes, for example, or simple people may propose that because you have a large loss, for example, you have a 30 dB loss, then if the input is 30 dBm, then output is 0 dBm. Then if you say that 0 dBm is not high enough, can we increase this 30 by 40? Then you get a 10. Yes, that is one way. But for these optics, we cannot have such a high power input. So it means that you cannot increase the input power to try to combat the loss by the system. Another thing is that the loss is huge, and the signal to noise ratio is poor. So you simply increase the input power, but the signal to noise ratio may not be good enough. So I think it's a simpler way to do it is that you have a link. You have, for example, you have a cable, and we try to reduce the loss to ensure that the signal can go through this cable easily without a lot of attenuation. And that is the only way. We have to reduce the loss. Yeah. Thank you for your question. And I think that is a solution. Sometimes that if the output is low, then we increase the input. It's okay. But for the real implementation, but the input the power may not be. You cannot arbitrarily increase it. Thank you.
Okay. So that's probably there's no further question. Let's join me to thank Professor YAO Jianping.
To express our appreciation to Professor Yao, prepare a small souvenir. Yes. So this is a special plaque just made for you. Yeah.
Thank you very much.
All right. I also would like to thank all of you for joining this lecture today, and also especially thank those who ask outstanding questions. So PAIR have organized regular seminars and lectures from time to time. Actually, this week we have 2 more to come up on Friday. Friday morning, we have a Professor Gao Jian from Tsinghua University, who is very famous. I think he is an academician of 7 or 8 national academies. So we'll give a lecture at the 10:30 a.m. And then his topic is related to the mechanics. So if you are interested, please join us. Then on Friday afternoon, I think at 2:30, we have a Professor David Pugh from University of Minnesota, who is also a member of the National Academy of Engineering in the US. We'll talk something about the air quality. Okay, welcome to the pair seminars and lectures. So this one is adjourned. I also wanted to thank Professor Li Chao, who organized this, and also Professor Jing Wei. Okay, thank you very much. Bye-bye.